Hi, we will continue our discussion on model evaluation metrics. By the end of this video, you will be able to explain and calculate R-square for a regression model and use it to evaluate and compare, and explain what is adjusted R-square and why we need it. Now, let's pause and zoom for a second and let's summarize the ground we have covered so far. We made regression models based on mean and visualized them. We also visualized the individual errors of these models with the help of residual plots. We learned about different metrics to quantify the error corresponding to our models. Now, all the evaluation metrics or measures of error that we have learned so far give us an absolute value for the error. Now we know that a model with smaller error is better than a model with a larger error term. But the question is, how much better? We also know that a model with 0 MAE or RMSE, that is when there is no difference between predicted values and actual values, would be 100% accurate. But how about a model with say 250,000 as MAE? Is there a way we can describe how good this model is in percent terms? Yes, there is another evaluation metric known as R-square, which does exactly the same. Instead of providing any absolute value for error, it gives us the relative error of a regression model with respect to the simple mean regression model. Consider that y bar is the mean of the sale price, y hat is the predicted values from a regression model, y represents the actual sale price. Then R-square can be defined as 1 minus sigma y hat minus yi square divided by sigma y bar minus yi square, where sigma yi bar minus yi whole square represents the n times the mean squared error of the simple mean model, and sigma yi hat minus yi whole square represents n times the mean squared error of the model that we need to evaluate. So, R-square can be defined as 1 minus MSE model divided by MSE mean. Now, if we focus only on the ratio part, what do you think it will tell us? It is the ratio of the mean square error of the regression model we want to evaluate over the mean square error of the simple mean regression model. The value of this ratio is expected to be as low as possible for a good regression model. Now, if we subtract this value obtained from the ratio from 1, we obtain the R-square value. Looking at the formula, we can see that when y hat is equal to y, that is, when the predictions are the same as the actual values for all the data points, the numerator would be 0 and the value of R-square would be 1, that is 100%, which indicates the perfect model since the predictions are same as actual values. Similarly, if y hat is equal to y bar, then the numerator is the same as the denominator and hence their ratio would be 1 and the value of R-square would be 0, which means that for a mean prediction model, the R-square would be 0. Accordingly, for any model which is better than mean prediction model but is not a perfect model, the value of R-square would be between 0 and 1 or 0% to 100%. It is worth noting that generally the range of R-square value is said to be 0 to 1, but in reality, R-square can take values from negative infinity to 1. The negative value of R-square is only possible when the regression model we are trying to evaluate is even worse than the mean regression model. So let's calculate the R-square of the regression models we have created. For that, we simply define the variables y as sale price, y bar as the mean sale price, y hat as the predictions from model 2, and n as the number of observations. Lastly, we check the length of each list, which turns out to be equal. Next, we calculate the mean square error of model 1, which is nothing but the mean model. Now, we calculate the mean square error of model 2. Now that I have calculated the respective values, I will simply put them into the formula of R square. We can see that for model 2, we get an R square result of 0.5 or 50%, which is quite good considering the simplicity of the model. So what exactly this R square value means? R square explains the degree to which your input variable explains the variation of your target or output variable. So if R square is 0.8, it means 80% of the variation in the output variable is explained by the input variable. So in simple terms, the higher the R square is, the more is the variation explained by your input variables, and hence better is your model. The R square is a quite popular evaluation metric since it gives us a measure of model error or model performance in percent terms, which is easier to understand and compare. However, the problem with R square is that it will either stay the same or increase with the addition of more variables, even if they do not have any relationship with the output variable. This is where adjusted R square comes to help. Adjusted R square penalizes the result for adding variables which do not improve your existing model. We will study adjusted R square in detail later at an appropriate place. For now, it is sufficient for you to know that as we keep adding more input variables to our regression model, the value of simple R square can no longer be relied upon and we need to make certain adjustments to it. With this, we come to an end to this topic. In the next topic, we will start linear regression. See you there.